Thank you, Ram, ROICE staff and membership for welcoming us, members of the Subsea Systems Institute, University of Houston, and thank you all for joining. We are honored to be here with you to open the 2025 ROICE Annual Workshop. I am Suzanne Chess, co-founder and managing director for Tiabzu. I lead a team of professionals whose life trajectories led them to join us in this endeavor. Presenting with us here today are my husband and co-founder, Bob Evans, Mike Edwards, and our lead engineer, Ryan Elliott, Dr. Andrea Neal, Environmental Scientific Advisor, Dr. Dan Tormey, and we will begin with Dr. Tim Forstmann.
Hi, I'm Tim Forstmann. It is an honor to share my marine experience with this august ocean technology community. As the former chief scientist for the United Nations Environment Program, I had the privilege of leading many global water initiatives. I started my career as a Navy frogman, having been personally mentored by Jacques Cousteau when I was a precocious 14-year-old at the Smithsonian Institute's Summer Oceanography Program. I was a pioneer in the use of satellite technology for Earth observation and oceanographic monitoring, with my first scientific paper on the application of satellites for mapping and measuring giant kelp, Macrocystis porifera, off of coastal California. My career using Landsat satellites for environmental protection and sustainable development led me to serve at NASA headquarters as the national chairman for the Digital Earth Initiative under Vice President Al Gore, which led to many developments, including Google Earth. With a master's degree in water engineering, I served the U.S. Naval Engineering Laboratory on many offshore and coastal research and development projects, including support for Hawaii's Ocean Thermal Energy Conversion Project. It is rather straightforward as to why Tiabzu has attracted my attention and support. From my perspective, global water supply challenges will continue to be a priority for a growing and thirsty world. Therefore, the innovative vision shared today represents a conservative target for financial and marketing fruit picking. Today, you will witness a brilliant demonstration of Tiabzu's creative engineering genius for the restoration, reuse, and regeneration of the near-shore infrastructure meet the demands for freshwater resources. It is intellectually stimulating to consider the ability to scale these technologies. The scaling and scoping of today's fertile technology discussions are profound with equally impressive entrepreneurial benefits noted for environmental protection, innovative marine engineering applications and operations, economically sound engineering savings for such operations, and unleashing viable new freshwater resources for global applications. In my opinion, these applications attend to the core ROICE model. As you listen, you will come to appreciate how the scope of Tiabzu's pilot and collaboration with transitioning offshore oil and gas entities will lead toward a solution for sustainable water supplies. You will appreciate the versatile configurations of the Tiabzu buoyancy control technology for global maritime applications. Again, consider the scoping and scaling of this unprecedented engineering capacity for myriad marine applications in the remnants of offshore energy infrastructure. Buoyancy control allows for launching with commonly available harbor ramps and cranes that not only lowers capital costs of implementation, but broadens accessibility outside areas of concentrated offshore resources. Versatility enables mobility response for humanitarian or emergency need or transport operations between islands or coastal communities, including support for forward operating bases. Tiabzu technology harmonizes with the global water supply security issues, as well as the environmental protection and sustainability goals of the United Nations. Tiabzu technology offers unprecedented new opportunities to support coastal communities in the U.S. and around the globe, creating a balance for economics, environmental, and social conditions.
Hello, this is Bob Evans, co-founder and system architect for Tiabzu. I spent countless hours daydreaming on Platform Hilda, visions for the future for these structures. As a platform diving pioneer, D.I. Bolding from Exxon USA invited us to establish an ocean observatory beneath this newly installed platform Hondo, the deepest platform of its time, 850 feet. Watching a reef form or time lapse, we could add up the benefits of this valuable resource. In 1983, with a Kennedy Celsius matching grant from NOAA, my team, the Mussel Company, successfully harvested and canned mussels, demonstrating the commercial viability of repurposing offshore infrastructure for aquaculture. Atlantic Richfield funded Man-Made Oasis, a multimedia presentation showcased at the Cabrillo Marine Aquarium in Los Angeles for decades. It introduced the world to offshore platforms as artificial reefs, sparking new perspectives on their ecological benefits and alternative uses. In 2015, Santa Barbara is in the midst of a severe drought. I was reading about the restart of the local community desal plant. I understood the process and its history. I wondered, why not operate subsea and use the natural pressure of the ocean for desalination? This would reduce energy demands and the environmental impact.
As much as 40% of the energy costs for desalination is not only for reverse osmosis, but also to power the high-pressure, high-flow pumps that move as much as 5 times the amount of seawater as freshwater through intake and pretreatment. Pre-osmotic filtering removes marine life and coastal particulate matter from the seawater. The residual brine concentrate is not only saline-rich, but also includes the remains of this biomass. This biochemical cocktail is discharged back into sensitive coastal waters. Phytoplankton is among the marine life entrained by intake and impacted by brine discharge. Phytoplankton concentrates along coastal zones. It is the base of the aquatic food chain and a primary source of more than half of the oxygen on the planet, releasing more O2 than all plants on land combined. Phytoplankton also absorbs CO2, which is delivered to the deep ocean depths when the life that feeds upon the carbon-rich phytoplankton descends. This is part of Deal vertical migration, a natural carbon sequestration that cycles from surface to a depth of 900 feet every 24 hours. DVM is a planetary climate regulating process that can be adversely impacted by nearshore seawater intake and discharge. Operating subsea, high-pressure, high-flow pumps required only for delivery of purified water from depth to surface or shore. Pumping only the product, the purified water, and not the product source, the seawater, lowers overall energy requirements by as much as 40%. Contributing to energy savings is removing multi-pump pre-osmosis by operating below the ocean's most biologically productive zone. Contemplated depths avoids the impact of desalination on phytoplankton, the marine carbon cycle, and potential negative feedback on climate perturbation that these systems can cause. And no one wants one of these obstructing the ocean view from their Malibu estate. Approximately 50% of the implementation costs for the Carlsbad, California facility is attributed to the regulatory process and mitigation efforts. NIMBY delays implementation for years and chalks up hundreds of millions in front-end costs. The assumption is that the removal of the environmental impacts from intake and discharge, as well as competition with high-value coastal real estate, will lower that price tag. We pulled in our favorite engineer, Ryan Elliott. We hired a team of process, structural, mechanical, chemical, and reverse osmosis engineers at IDI in Knoxville, Tennessee, to design the Tiabzu system.
Hi, I'm Ryan Elliott, mechanical ocean engineer, diver, and licensed professional engineer. I began working with Bob and Suzanne on various projects while in commercial dive school and continued while studying mechanical engineering at Cal Poly San Luis Obispo. Our collaborations continued after graduation while I worked for other companies on various ocean engineering projects, including subsea power infrastructure, ocean observatories, and subsea sensors for the United States, the United Nations Nuclear Test Ban Treaty Organization, and other customers. I also participated in the installation of these projects as a diver, deckhand, or equipment operator, in addition to the engineering, testing, and equipment assembly phases, giving valuable field experience to incorporate into subsequent designs. When we began looking into deepwater desalination, we learned that the primary challenges do not lie with the desalination process. Hydrostatic power-driven reverse osmosis is disclosed in patents issued to Lopez Ferdinand in 1980. Subsea desalination was piloted in the late 1990s by a team of researchers in Italy led by Paolo Pacenti with the European Commission. More recently, a team in China led by Huifeng Cui from Hainan University piloted a turbine-based energy recovery scheme for a reverse osmosis system designed to operate at 1,100 meters and provide fresh water to China's proposed deep-sea space station. GE Water and Power Technologies, now Suez, Siemens, and IDE investigated subsea desalination using methods of DXV water technologies. Efforts were abandoned when confronted with the economics of subsea implementation and operation, such as the cost of specialized vessels and cranes for installation required for their approach, equipment recovery for maintenance and removal, regulatory costs, and how to deal with silt and biofouling. Tiabzu addresses these challenges with its unique approach to deployment and recovery from depth to surface for maintenance or at end of life, and a patented system for buoyancy control. While Tiabzu can deploy using an A-frame or deck crane, it can also launch from commonly accessible harbor facilities and be towed to the installation location. Reducing the size of the handling vessel promises to shorten the time for implementation and avoid costly scheduling delays for heavy lift vessels and cranes with their limited availability and high demand. Not to mention removing their high cost, estimated to start at $200,000 per day, from capital expense budgets. Tiabzu brings the tools, technology, and methods to change the environment for desalination. We leverage natural processes, deep ocean hydrostatic pressure for reverse osmosis, relative density between freshwater and seawater for buoyancy control, and symbiosis with existing offshore infrastructure to make subsea desalination competitive. Planned operational depths for the Tiabzu system are between 410 and 610 meters for water pressure-driven RO, below the ocean's most biologically productive zones. This reduces the requirement for pretreatment. High-volume flow-through limits concentration of extracted salts and suspended solids. Energy savings is a result of only pumping generated fresh water to RO pressure versus conventional systems requiring pumping 5 times the generated freshwater volume up to RO pressure. Operations shallower than 410 meters require additional pre-osmotic pumping similar to conventional systems. This buoyancy system integration is used to facilitate deployment, recovery for maintenance or at end of life, or to position and maintain it at operational depth during mobile operations. For scaled water harvesting fields, the module keel will mate with subsea infrastructure. The Tiabzu system includes an integrated buoyancy control system analogous to a hot air balloon. Using difference in density between hot internal air and cool external air for its lift, its balloon or bladder provides lift using the approximate 3% difference in relative density between the RO water and seawater. RO water buoyancy allows safe vertical movement of subsea objects without change in lifting force with depth associated with gas-based methods where buoyant force varies with changes in pressure.
I'm Dr. Andrea Neal. I'm the president and founder of Blue Capital. I met Bob and Suzanne back in the day when I was working with Jean-Michel Cousteau and working heavily as a scientific diver. Over the last 20 years, I've led major expeditions across the Atlantic and the Pacific and throughout the Sargasso Sea, as well as accomplished many feats in the waste-to-energy industry, including large-scale industrial production of waste-to-energy facilities. Today, we're going to go through some of the things about Tiabzu, objectives, pilot scale, and replication of the project. The plan is to deploy a commercial scale system next to a platform and conduct a pilot for a minimum of 6 months to confirm predicted operational efficiencies, energy, environmental, and economic outcomes to de-risk the project for financing and performance insurance. This de-risking step allows for easier project finance capacity for industrial, commercial, and government clients to include the Tiabzu system and water supply portfolios. The first stage of the pilot will be to saddle a remote operating vehicle with a small-scale desalination system. The ROV will carry the system to its operational depth and run through the paces to demonstrate system efficacy, operational hours for insurability, and using the generated freshwater as a form of buoyancy for recovering and positioning the module. Successful phase 1 testing and analysis will raise the technical readiness of this system for commercialization of mobile operations and subsea lifting, such as salvage, defense recovery, and heavy lift operations. Co-locating with existing infrastructure will lessen time for planning to production at a much lower capital expense. Shallow locations such as Gulf of America can be accessed with additional pre-osmotic pumping.
Hi, this is Mike Edwards. My oil and gas career spanned 4 decades, beginning as a field landman before various promotions where I worked in acquisitions, legal, government relations, community and public relations, and finally in investor relations. Besides many years living and working in Santa Barbara, I spent a considerable time on boats in the channel going to and from platforms. I was also very fortunate to join the UCSB Marine Research Team in a 2-person mini sub and saw the abundant sea life on and at the bottom of Platform Gale in 740 feet of water. Approached the repurposing of offshore infrastructure as a collaborative process, working together with owner-operators, leveraging their assets, and having a positive impact on their bottom line. The Tiabzu system is designed to operate independently without any interference with platform operations. The system is cross-supportive with power supplied from the platform and fresh water supplied to owner-operators. This symbiotic relationship establishes a framework for development and regulation for long-term uses. This alternative use for the offshore infrastructure provides a transition as conventional productivity declines. And in the case of Tiabzu, as alternative energy sources come online, the possibility of keeping the assets productive for a longer period. This transformation can create a new and sustainable offshore economy. We use California for economic modeling because it is home to most of our team and where we're most familiar. It has a clearly identified need, multiple sites with suitable bathymetry for post-pilot scaling at required depths, and near-site existing infrastructure. Since it is also one of the most regulatory restrictive and expensive locations to implement and operate, we believe our predicted returns are relatively conservative. Frankly, if this can be done in California, it can be done anywhere. We have identified and will continue to source other locations globally and invite input. We have patents issued in strategic regions internationally. Levelized cost of water, the LCOW, is used as a standard performance metric, and we use those suggested by Sandia National Laboratories. We added DT, development, to the initial capital costs to account for the project's iterative stage. We are looking forward to seeing how these values hold when updated using Dr. Seetharam's techno-financial modeling here at ROICE. The basis was an initial bill of materials for the pilot and energy required for mean output of 500 gallons per minute, which is the pump chosen during concept design. Pump range is 250 to 1,000 gallons per minute. As we scale, we shift the pump output to the maximum volume of 1,000 gallons per minute, as adjusted by an 85% operational efficiency. Dependent variables are module scale, number of modules, operational efficiency, and site-specific power source. The excess power capacity available at one of our modeling sites supports scaling to 100,000 acre-feet per year. Pump choice and energy requirement has since changed positively for the bottom line, but we kept initial feasibility values since for our purposes, conservative outcomes are preferred. Our financial models predict a doubling of profits within 5 years of approvals to scale up operations. Subsea Desalination produces high returns despite a low commodity price. less than 42 cents a barrel, as compared to oil at $70 per barrel or natural gas at $40 per barrel of oil equivalent. That price difference is offset by higher production volume of a non-depletable resource, plenty of seawater, coupled with lower energy costs and the efficient design of the Tiabzu system for low capex and its ongoing effect on the LCOW. Co-development provides the framework for regulatory or independent operations before momentum for decommissioning takes over. The alternative use provides the non-depletable assets for transitions as oil and gas productivity depletes and as other energy sources, wind, solar, hydrogen, wave, come online.
It doesn't have to stop here. As the ROICE model reveals, stacking collaborative assets increases profitability of repurposing. And subsea desalination is a keystone asset. It is cross-supportive of offshore oil and gas. It is also in line to support a variety of other uses. Feedstock for electrolysis, on schedule for discussion this afternoon, cooling of data centers, green hydrogen, or our favorite, sustainable mining of ocean water for minerals.
Hi, I'm Dan Tormey, Managing Director of Catalyst Environmental Solutions. I'm an internationally recognized environmental expert with a PhD in geochemistry from MIT and a BS in civil engineering from Stanford. Over the past few decades, I've worked across sectors, from founding a 40-person consultancy in California to serving on the board of an Australian circular economy startup. I also maintain an active research program in volcanology and have long-standing involvement in nature conservation. Today, I'm excited to share how our work is advancing the frontier of sustainable resource recovery from the ocean. So now, sit back. I want you to imagine a seawater desalination system that does more than just produce fresh water. With reverse osmosis, we create a concentrated brine stream, normally discarded. But in the right locations, near mining runoff or volcanic coasts, this brine becomes a resource. Lithium, copper, magnesium, even rare earth elements can be recovered. We're using the planet's own energy systems, wind, sun, ocean pressure, to harvest pure water and valuable elements from the sea. It's an elegant synthesis, sustainable energy powering circular resource recovery. This roadmap shows that many metal recovery technologies are already at a pilot scale and readily integrated into modular RO systems. With the right partners, these platforms can scale up quickly. This shows we're focusing on coastal regions where metal-rich waters are naturally concentrated, such as volcanic island chains and mining outfalls in the Pacific and Indian Oceans. Offshore platforms, some already built, can be repurposed into hubs of circular production, clean water, green hydrogen, and critical minerals, all from seawater. This isn't a pipe dream, it's a platform for the future. Let's unlock the hidden value in seawater together.
There are real benefits to subsea desalination. Energy and environment can be attributed to the operational setting. The real challenge is economic, and the solutions are the same for most, if not every, subsea development. Paramount is how to get equipment through the water column down deep, operate and maintain in this remote environment, and how to bring equipment back up when required, whether for maintenance or at end of life. A key factor is how to handle variable pressures, which comes down to buoyancy control. Methods currently used for deployment and removal are lift vessels and cranes and airlift bags. Heavy lift equipment is expensive and limited in availability, particularly in places like California, which is outside the concentrated offshore oil and gas activity, such as in the Gulf of America, North or China Seas. Air or gas-filled bags are sensitive to changes in pressure. Freshwater is safer, more stable than gas-filled bags, and is much less expensive than heavy lift vessels when processed and filled on site and at depth using the Tiabzu system.
Subsea, surface, and umbilical are the major systems of Tiabzu. The subsea system is composed of the RO, maneuvering, power and telemetry, and control subsystems. The reverse osmosis subsystem generates purified water from seawater using reverse osmosis membranes bundled in housings. The next slide describes this system in more detail. The maneuvering system carries the subsea system to operational depths and maintains system depth using a patented purified water buoyancy system. The maneuvering system contains a large bladder of fresh water, providing fine buoyancy control using the difference in density between seawater and freshwater. Overall system buoyancy, positive, up, neutral, stationary, or negative, down, is controlled by changing the volume of purified water in the bladder. Small changes in buoyancy are possible, allowing precision control and safe movement between operational depth and the surface. Purified water from the RO system is either sent to the surface or sent to the bladder to increase positive buoyancy. Fresh water is released from the bladder to decrease buoyancy. Thrusters allow lateral motion of the subsea system. The telemetry and control system contains the command and control systems for RO and pumps, control of lateral thrusters, and status of all systems. Data from instruments will be transmitted to the surface by the telemetry system, including water quality, depth, heading, environmental conditions, and any other qualities determined necessary. The power distribution system to pumps, thrusters, and valves is directed by the control system and will likely occur in a separate pressure vessel to minimize noise issues and better address thermal management. Power transmission from surface to subsea will likely occur at higher voltages and require conversion to usable voltages. The surface system consists of the operator interface, local command and control functions, and power supply. Telemetry and environmental data are displayed and recorded at the surface. Subsea system movement is directed from the surface station. The umbilical connects the surface system to the subsea system. The umbilical contains an air vent, water product line, power, data connections, and the strength member. Key components of the Subsea Tiabzu RO system module are the RO membranes, membrane flush pump, extraction pump, and RO water receiving tank. The umbilical contains a snorkel or vent line connecting the RO water receiving tank to the surface, maintaining the RO water receiving tank's internal pressure at surface atmospheric pressure. The produced water side of the membranes are connected to this receiving tank. The difference between surface and ambient pressure drives water through the RO membranes into the receiving tank. A low-pressure membrane flush pump ensures a fresh supply of seawater surrounds the RO membranes and helps disperse the higher salinity discharge from the system. An extraction pump draws purified water from the receiving tank and pumps it to the surface or shore, or, with the switch of a valve, into a bladder to add to the subsea system's buoyancy. An air-based ballast system is used during initial deployment. Once at operational depth, the RO buoyancy system is used for recovery for maintenance or at end of life, or to position and maintain it at operational depth during mobile operations. For seabed operation, the module will be negatively buoyant when the bladder is emptied, allowing the keel to rest on the seafloor or mating subsea infrastructure and resist disturbance or motion. This patented system integration is expected to significantly lower capital costs associated with implementation and address regulatory requirement for removal at end of equipment life.
We invite you to join on this journey, and on behalf of the Tiabzu team, I thank you.